So welcome everyone to the second seminars of our series, winter series for the Center of Mobile, Wearable Systems and Augmented Intelligence. The center is kindly funded with a donation from Nokia Bell Labs. The speaker of today's talk, which will be recorded and put online on the center's page, is Juan Ye, and she's a senior lecturer in the School of Computer Science at the University of St. Andrews. She has a PhD from the University College Dublin from 2009, and her talk is very much on around her interests related to human activity recognition, domain adaptation, continual learning, and unsupervised learning. So after this, I'll let Juan talk.
Okay, thank you for the introduction. And I'm very pleased to discuss our recent work in domain adaptation in human activity recognition. So human activity recognition is about inferring the activity labels from sensor data. The sensor data can be wearables or ambient sensors. And if we all think that in a very simple case, is a classification problem, right? From raw sensor data to active labels. Because of the sensors, we can see sensors are deploying many of the real world environments now in our mobile phones, smart watches. So it has lots of interesting applications in smart home automation and personal health monitoring. So because of this significance in real world applications, human recognition has been really heavily researched, and we have very well established methodology. We can start deploying sensors, collecting the sensor data, annotating sensor data with active labels. Once we have that, we can train a model, right? And the model can be deployed, and we can start recognize the new activities. So lots of, over the course, lots of data-driven and knowledge-driven techniques have been applied. For example, from the early stage, we have ontologies, and then we have hidden marker model, and more recent deep learning techniques. So all of these techniques have achieved very promising results. They can learn very complex coordinations between the sensor data and activities. So what's the problem then? Because most of this work require well-annotated training data, and the training data is really difficult, and this annotation is really difficult, and sometimes it can be more difficult than the image annotation. So for example, giving you an image, you can tell it's cat or dog, you can do the annotation, but I give you the raw sensor data, you might not be able to tell, oh, this person is cooking and this person is running. So it's very difficult. And normally there are only two ways to do the sensor data annotation, either annotated by the user themselves, but it can be very sparse and it can be very imprecise, or it can be annotated by a third party, for example, using the videos to record what the user is doing. Then you have a third party annotator to annotate what they are doing, and then you can match it to the sensor data. But this has a huge privacy implication. So none of them is ideal. And as we can see, the other problem is, even though we can do this sort of annotation, but we can't replicate the same process on many of the users. Right? You can't imagine every user will give you the sort of the same level of annotation all the time. That's very difficult. Okay. So the other problem is, even though we can learn get good annotations and train a good model, and when you deploy in the real world, what about the user start doing different kinds of activities? Then you need to go back to the original process and then collecting data annotation again. So it's very expensive and very tricky to do. So what we're trying to do is, we want to build accurate activity recognition model to support a large number of users and over a long period of time. And ideally, we want to reduce the annotation effort as little as possible when they are deployed in real-world environment. That's our goal. And over the time, we have tried different techniques. We have designed semi-supervised learning and unsupervised learning techniques, but all of them still require a certain amount of annotation from individual users, and this number is not very small. So give you an example, if we want to do the unsupervised learning, what are we gonna do? Give it the sensor data, you identify different patterns, but you still need the people to attach the activity labels on each of the patterns. That is the cost. So what about domain adaptation? Rather than think about individual users, we think of them collectively. And domain adaptation is a very popular research area in machine learning. The basic idea is we adapt the knowledge from one domain to the other domains. So in human activity recognition, we consider two different settings. The first setting is multi-source. So suppose here we have 3 data sets, D1, D2, and D3. And each of them are very sparsely partially labeled. And idea is we want to combine all their data together to annotating all the other unlabeled data. The challenge here is we don't mandate each of the data set has the same feature space. So maybe D1 has 10 sensors, D2 have 20 sensors, D3 maybe have 100 sensors, and how we mapping them. And the second challenge is their label space can be different. So maybe D1 has 3 activities, and D2 have 5, D3 have 10. So they are different. Even for the same activity, they may have different names or labeled tags to them, and how we can resolve that difference. And thirdly, we say partially labeled. That means even for D1, if we say they have 3 activities, but only 2 of the activities has been labeled. What about the other one has not been labeled? Can we using the D2 and D3 labels to complement the labels in D1? So this is the challenges we're going to tackle in the first setting. It is slightly different from the traditional machine learning multi-source domain adaptation. And that assumption is you have D1, D2, D3, they are kind of labeled all the activities, all the classes. The idea is only combine them to form a more robust classification model. So, but our assumption is much harsher than that. Okay. The second setting is a more traditional domain adaptation setting. So assume D1 here is a source domain. We can think about that in human activity recognition is a well-controlled environment. And the idea is we have all the sensor data being collected and we can annotate them in a very detailed way. The idea is how we can apply the model we learned on the source domain to the other 2 target domain. And both of D2 and D3 are not labeled at all. How we can do that? So for these 2 settings, we have developed 3 techniques. The first one, excellent, is targeting the multi-source domain adaptation. And the UDA and the shift GAN is more recent techniques to tackle the source to target domain adaptation. So we're going to introduce 3 of them. Start with excellent, and this is just a more detailed example of the problem we're trying to deal with. By the way, the excellent is more tackled on the binary sensors, it's not on the accelerometer data. So we have these 2 houses, house A and house W. As we can see, their spatial layouts are different. The number of sensors on each of the environment are different. And then we have the sensor data. The house A has been annotated with 2 activities on 6 data points. And house W also have 2 activities being annotated on 6 data points. And theta here means unlabeled data. So the idea of excellent is combine of this 12 data points together, and we're trying to annotate all the other data points. So you might find out here, this data point might map into, you might using the sleep labels from the other data set to label that. So the main idea of excellent is how we can share and complement labeling between each data set. So the problem we're trying to deal with is, the first one is how we can map into different feature spaces because the sensors are different, how we can match them. The second one is the label spaces are different, how we can mapping them. Then the third one is how we can learn, how we can share the labels between the data sets. We're going to tackle the feature space and label space remapping using the knowledge modeling. So because we are dealing with binary sensors, then we can using the knowledge. The binary sensor has knowledge. Each binary sensor is normally attached to a certain object and they put in a certain location. So the object and the location are the semantics of sensors. And with that, we can build a similarity between a pair of sensors in different domains. So for example here, this is the WordNet ontology. It's not a full set, it's only part of it, just showing how it works. So you have the cup, this is the objects the sensor can be attached to, and then that it can be organized into this hierarchical structure. And the bottom is the location ontology. As you can see, this is slightly different. It's very generic smart home and location ontology is based on the functionality. So for example, the bedroom here is a type of sleeping area. We are not using the spatial layout. For example, we are not saying the bedroom is in the first floor and living room is in the ground floor, because that kind of modeling will be very specific to individual environment. And we want to reduce the knowledge engineering effort as much as possible. So with these two, the WordNet, that can be generic, that's already generic. And this location ontology is also generic. We can use the same ontologies to all the environments we're going to test on. So with these two ontologies, then we can calculate the similarity between the sensor data. So that is here, for example, we can calculate different sensors in two different environments. And with the sensor similarity matrix, we can map in the sensor features from one environment to another. And we can also calculate the similarities between different activity labels. For example, this is the house W activity labels, and this is house A activity labels. And we can see the live home is very well matched to the home in another data set. But the problem is the ontologies we're using is very generic, and we don't add in any more constraints or rules on the activities. So that makes the mapping can be very rudimentary. For example, this sleep activity in house A can map into two activities in house W, resident 1 sleep and resident 2 sleep. And then we'll have more problem with mapping the meal preparation with 3 activities in house A here. But we don't do anything to do that for that, because the problem is we still want to keep the knowledge and engineering effort as little as possible. And we see how this kind of small knowledge can apply into the multi-source domain adaptation. Okay, so now we can map in the sensor data from one environment to another. The next step is we're going to build individual activity models first for data set D1, D2, D3. Because the assumption is each of them only have very scarce labels. So how can we make most of it? And our first step is using the clustering algorithm. So for example, here, these labeled data points is clustered with another 3 data points. And then we push the label to all the data points within the same cluster. And in this way, we can extend our training set. So, and the second step, once we build the individual models for each of the data sets, our next step is, what about these clusters with all the unlabeled data points? And we can try to query each of the activity label models to get the labels for them. But the problem here is, what's the best way to do that? We can using the majority voting. So for example, for each data point, we send it to each of the data set and asking for labels. But the problem again, because our assumption is very scarce labeled data, then each classifier on this kind of data set can be very biased to their majority classes being labeled, or give you very inaccurate classification results. So we can't use the majority voting for that. And then the alternative here is we use the stacking ensemble method. So to do that, we will, for each of the data set, for all the unlabeled data points, we will generate the meta features first. The meta features have 3 different types. The first one is the posterior probability to tell you how confident each model infers activity. And the second one is the model accuracy itself. How accurate this model can infer this activity. That's based on the training data they have itself. They can tell you how, given this data, how accurate I normally do. The last one is based on the distance to prototypes, to the clusters, how closely each of data points to the largest cluster they have, to all the clusters they have. So using these meta features, we build another classifier, and we can train on all the labeled data points. And with the build stacking ensemble, we can also go back to label all the unlabeled data points. Okay. So we test our approach on 4 data sets. And the first 3 data set house ABC are quite small. They are from the University of Amsterdam. And the last data set is from Washington State University, the CASAS data set. It have 2, is 1 year, the data is collected from 1 year student apartment, and have 2 users, have 2 residents in the house. And we're using 13 app classes from that data set. Okay. So let's see the overall accuracy between the excellent and some baselines. So we consider 3 baselines. The first baseline is just training on whatever being annotated. That kind of give you the idea how terrible the algorithm can work. And the second baseline is called training, and that is a very classic kind of semi-supervised learning method. You start with a very small set of annotated data, and you build a model, and then using that model to annotate all the other data in the unlabeled data pool, and then sample them out and incrementally enhance your algorithm. And active learning here means you can query the users for the data point you are not sure. So in comparison, the baseline and cone training does not work well because, like we said, we only have very scarcely labeled data, so they can't get new annotations for the data they have never known. They don't know the, so for example, if a data set only have 2 classes being labeled, then it doesn't matter how you're gonna learn them, you can't learn the third labels. But active learning can work well because it can query the users for the third classes has not been labeled. But the problem here you see, this is why we said semi-supervised learning may still incur a high number of annotation. So the active learning will query the percentage of query is between 10% and 20%. So with a 500 data point data set, then you can see that we'll have 100 data points needs to be annotated. That's kind of a lot. The third observation we can see over time, excellent will outperform active learning. When they accumulate enough data points, it will be better even than the active learning. Especially on the house W here, the reason when we debugging the results, analyze it, we're finding out because the house W has slightly higher dimension, have 83 sensors, and the data is also very noisy because they have two residents in the data is being collected, and the uncertainty sampling techniques does not work well. They can't find the meaningful samples for the user to query the users. So even though you have this active learning, you query the users a lot, the active learning still cannot achieve high accuracy. And that is overall performance comparison. We're also looking at the impact of heterogeneity between the domains. Because the assumption is the similar the domains are, the more likely the accuracy of using these domains will be higher. So here on the house A, we compare the accuracy between different domain combination. So we start with AB, ABC, and AW, because W is the most different one, and we expect the results on AW will be worse. And the results kind of showing that. And here we present 3 different types of accuracy. The O is instance accuracy. F1 here is class level F1 score. And S here means the similarity scores. So even though we can't predict the exactly same labels, but if the labels have very high similarity to the ground truth labels, that will contribute to that. So F1 score will be the harshest measurement, and S is the easiest one to achieve. So at the beginning, when the data points are very small, as we can see, the more data we have, the higher accuracy will be. So ABC will achieve higher accuracy than the others. But over time, there's not much difference between ABC and the AB combination because they are all quite similar. But there's a large differences between AB and AW. You can see AW combination still does not give much higher accuracy than the AB. But actually, over time, when the training data points accumulate to a certain degree, there's not much difference anymore. And this shows the house A is more likely to using its own training data to get labels rather than querying rather than getting the labels from house W. So that's a kind of way to prevent negative transfer from the other data set. So since this kind of works well with very small data points, the next step is, can we push it even further? So we assume all the data points for all of these data sets, none of them are annotated. Can we using this XLearn to help us select data points for annotation? So to do that, we design another experiment. For each of the data set, we do the clustering. And then we order all the clusters in a descending order, with the largest cluster first and the smallest cluster later. So by selecting the data points is, if each data set can have 2 annotations, then we're choosing the center of the 2 clusters, the first 2 clusters. And if we can go down the list later on if you want more data points being annotated. And this will give us very interesting results. As we can see, with only 2 data points being annotated, we can have nearly 70 or 80% of accuracy on house B and C, because these 2 data sets are very highly imbalanced. So the accuracy on these 2 can be very high if you're choosing the majority classes. But actually, if you think about the F1 score, they are kind of similar to house A and the others. And for house W is much lower because they have more classes. And another interesting observation we can see here is after maybe around 14 or 16 samples from each of the data sets, the accuracy is already reached to the best performance. But for house W, maybe takes slightly longer. That one maybe with 38 samples. But this is a much smaller number compared to the active learning, the query percentage. 38 out of 70,000 data points is much less. Okay. So coming to the excellent again, have we resolved our, have we addressed our research questions? Is it scalable? We can see excellent can achieve satisfactory accuracy when there only exists a very small number of labeled data in each data set. And it can scale to many users. Actually, the more the better, because the more data set you have, then maybe you can, your training data set will be much larger. So you only need each user contribute to very small samples. And does it help with long-term activity recognition? What about the user doing new activities? We can still do that, but the overhead would be we need to retraining the stacking ensemble with the new activities being labeled. And the computation is quite cheap. The clustering, we're only using the k-means, and with the classifier on each data set, and also the ensemble, we're using the naive Bayes. It's a very small size of the model, and the training is really fast. And do we have to use XNM for whatever the situation? And the answer is probably no. Once you use the XNM to accumulate enough annotation on each data set, you can change it to another more sophisticated machine learning techniques to improve the recognition accuracy. So a limitation is also obvious. As we can see, the knowledge modeling is very crude. It's not accurate at all. It's not accurate for feature space remapping, definitely not for the label space remapping. And it also still requires knowledge engineering effort. Even though how small they are, you probably still need to ask for each data set to annotate which sensor is attached to which object and is put on which location. And you must have that. And also if the sensors has been moved from one location to another or dislodged, then the method does not work. So because of these two limitations, we developed another two techniques to resolve them, is WUDA and ShiftGAN. So WUDA is, both of these techniques are working on the traditional domain adaptation scenario. So for WUDA, the idea is we start from labeled source domain. That's what we think is a control environment. And we collect data, have all the labels, and then we try to adapt the model to unlabeled target domain. And we try to use the in-class alignment. The idea is for all the running samples, we align with target domain on running samples. And we align the working samples from source and target domain. So, but the problem here is because the target domain is not labeled, then our first task is to generate pseudo labels for target domain. The idea is because the source domain is labeled, that's easy. We can build a classifier on the data. And then we can use the excellent method, the sensor similarity, to translate the target domain data into source domain. And then using this classifier to annotate all the data points on target domain. So that's how we get pseudo labels from the target domain. To do the in-class alignment, we're using variational autoencoder. So the idea is for each of the class K, we train a variational autoencoder, and then hopefully we can get a very robust latent representation on the source domain data. And to do the alignment, we copy the encoder to a new network. And we're using the target domain transfer to the source domain, this data, and putting the data through, we trying to minimize the difference between the source domain data and transformed target domain data, and making sure the difference on the when they project on the latent space is very small. So that's the idea. So once we have that, then the rest step is very straightforward. Then we can just build a classifier on the source samples when they project in the latent space, and using that to annotate all the projected target samples. So as we can see the results, here is our approach is in average, in general is much better than the state-of-the-art and transfer learning techniques that are working on the heterogeneous feature spaces. And in some cases, much worse. For example, when we do, oh, sorry. This is the house ABC we have talked before. And Aruba R1 is from the CASAS dataset. Yes, of these two datasets, UDA, there's 2 occasions does not work better than the state-of-the-art techniques. And the situation, analyzing the results is the same. From R1, R2 are the smaller dataset. Aruba is much larger. It's 2 times than R1 and R2. So from a smaller dataset mapping to the larger targeted data, UDA does not perform well. I think the main problem is lack of enough training data from the source domain. And the other thing is we want to see whether this kind of high accuracy is because of the magic behind this kind of deep learning method, variational autoencoder, or is it kind of some meaningful results within them. So to analyze that, we project the source and the target domain data into the latent space, and we see if they mix up or not. So as we can see here, each we look at 3 classes, and each symbol here represents one class, and the color represents different data sets. And with the UDA method, both source domain and target domain data mix well in the latent space. But with the TCA, the classic transfer learning techniques, we can see these data points are still very separated between each other. So in that case, we think this UDA can help, can improve the feature space remapping with the variational autoencoder. And this in-class alignment actually can boost the active recognition results. But that's not solve the problem with knowledge engineering effort. We still need the knowledge modeling to build the first step. So how can we get rid of that? And then that leads to our latest work with the shift GAN. So the GAN is generative adversarial network. The basic idea is in GAN, you have 2 networks, generator and discriminator. Generator's job is trying to generate the data as close to the real data. Discriminator wants to tell the difference. So until the generator defeats the discriminator, that means the generator can generate data very close to real data. Okay, and this GAN has in image-to-image translation, they have this called bi-directional GAN. For example, dual GAN here. So the idea is they can translate the images. This is sketch. This is a real photograph. So they can translate this sketch to a real photograph and coming back. So you can think about this F and G here are the generators from 2 GANs. So taking the sketch, you using the generate F, generate the photograph, and then using the generator G to coming back. And the job here, the objective here is trying to minimize these reconstruction errors using these cyclic constraints. So The idea we're trying to do here is we can maybe using this image-to-image translation, taking the sensor data from house A as a sketch and house B data as a real photograph. So we don't need any knowledge. We can just play with this cyclic constraints and the loss to making sure we can translate house A data to house B and then vice versa. So this is how we using this bi-directional GAN to enable heterogeneous feature space remapping. But because GAN is well known to be noisy, and the sensor data, we don't like have an image to inspect, oh, this is a good translation, or this is a bad translation. We can't do that. So instead, we're using the kernel mean matching. That is a non-parametric distribution matching techniques. That's a traditional use to, so you have training data and testing data. And the idea is you learn the weights on the training data to making sure the distribution between training data and testing data is very small when they match into the RKHS space. So here we, after using the bi-directional GAN, we're using the kernel mean matching to further reduce the difference between the source and the target domain features. So now, since we get rid of the semantics, then we can do more domain adaptation, not only on the binary sensor data, we can also working on the accelerometer data. So for example, we can working on these sets and PAMP2 accelerometer data sets. Okay. Okay, this is our comparison results. Because most of the data sets we are playing here are imbalanced. So we're still using the class level F1 scores as accuracy measurements. In the blue boxes are traditional transfer learning techniques, and in the green boxes are more recent deep learning techniques. And we think 4 of them, AD-ADM, DAN, ADDA are adversarial techniques because shift guide is kind of in that domain. So we can compare with them. And by comparing with them, we're trying to understand whether this bi-directional GAN is better than the single GAN or not. And based on results, we can see shift GAN consistently better than the other 3. So we think this bi-directional GAN maybe can generate more robust features than the single GAN. And compare with DAN is a deep annotation network. We don't have much better accuracy in the binary domain adaptation tasks. And DAN is working much better than our technique. But when the dimension goes up, going to the accelerometer data, our technique works better. And the reason is that this is a DAN architecture. So the idea is you have some convolutional layers and you have fully collected layers for source domain and target domain. And then we are doing this multi-layer, multi-kernel MMD matching. So they were looking at each layer, how you can reduce using multiple kernels to reduce the differences between the layers. So this is kind of putting the, they are more working on the model level domain adaptation, but we are more working on the sample level. So maybe it's more, how to say the word? It's more, it's not as stable as they are, let's say, putting it that way. And their method works well on the small, kind of small dimensional data as we have. It doesn't work really well on the accelerometer data. We don't know why yet, because their method are proposed for the image data. So there must be something we're missing. Because of GAN has problem with convergence and training time. So we compare the training time with shift GAN or all the other techniques. On the accelerometer data, shift GAN is kind of okay. It's only taking much long and taking slightly longer than DN, but much better than the other techniques. With the binary, it works in the higher spectrum, but it's not too much. So for each training task, we're taking 3 minutes for training. And in terms of convergency, here we plot the loss performance on the primary generator and discriminator for tasks DS-ADS to PAMP2. So that's between dimension 405 and 243. So we can see the model actually converges well because the loss does not change much, maybe after 600 epochs. Okay. And we also test on the sensitivity of training data on target domain. So if we're using 20% of target domain data in the training, would that kind of lose lots of the recognition accuracy? But actually, as we can see, the accuracy is quite stable on different training percentage. It's not only with the shift gun, with all the other techniques as well. This may be showing some kind of promising for the feature and domain adaptation. That means we don't need to collect a lot of data in the target domain to do this domain adaptation. Maybe a small number of data that can allow the quick adaptation. And we also test on the sensor noise. So the idea here is we randomly sample 25% of features of the sensor features and adding the Gaussian noise and see only in the test data, see how the algorithm responds. But actually, our technique shift gun works the worst in a sense. It kind of decreases over time. The more noise we add, the worse it performs. But with the other two deep learning techniques, they are more stable. Again, because the DAM can compels do the domain adaptation on the model level, so they can be more stable than us. But we are working on a sample level. Even the sample distribution has been changed, the accuracy will drop. And that's something we need to working on in the future. So working in the future, we have designed 3 domain adaptation techniques so far, and they're working on different settings. For the first setting, the multi-source setting, we think XLAN has, I think that's a very interesting, promising scenario. If we want to do the large scale, the data collection and activity recognition, and we can just leverage the sparse annotations from each users. But the problem here is still the knowledge engineering is a bottleneck. And we need to find, if we want to working on the accelerometer data, we need to find another way to do the mapping. For the setting 2, the traditional source target domain adaptation, UDA and shift gun has more powerful learning capability than XLAN and has achieving good results compared to the latest transfer learning techniques. The feature alignment is definitely more accurate than XLAN. But the problem here is we might need to improve on class level feature transfer, especially on the shift gun, because they're taking all the sensors and all the data sets to do the feature mapping learning. We are not working on the in-class level feature transfer yet. But again, that's in our future work. And we are not very, we're still, the techniques are very sensitive to the data noise. That's something we need to work on as well. And the last future work is we are only now consider each data point, the features as snapshot, and we don't consider the sequential features, the temporal features yet. So we're gonna include that in the future. So this is, and the most of work is done by Andrea and our 3rd-year PhD student. She's very clever. She designed all that, the UDA and the shift gun techniques. And the others are the PhD students and collaborators that help forming the ideas over time. So That's all.
Thank you very much, Erica. It was a wonderful presentation, so I'll clap for everyone. As suggested by Dong in the chat, if you want to ask a question, you can just put it in the chat and I'll read it out to Erica. In the meanwhile, I will ask a session, a chair question, which is, okay, you've presented various techniques and you have applied them to HAR data. I wonder how much of your approaches are generalizable beyond HAR data in general. You showed a couple of binary examples, but I wonder if you can elaborate on that, if the novelty of some of the approaches would be applicable to other scenarios just because of the similarities of the type of data or other reasons?
Yes, that's a very good question. Actually, we want to branch out more into the machine learning area. So because the work is done in recent 1 or 2 years time, and it's mainly started from my part because I'm very familiar with the binary data set. So we always start with that. And XLAN itself, I haven't figured out a way to apply to other data sets like image or text data, because you need that sort of pre-mapping first. But actually with the shift GAN, I think there has more potential to be applied to other types of data. We want to try on the text data like a office data set in the future, but we haven't got a chance to do that yet.
Okay, thank you. I don't see any other questions in the, oh, there is a question in the chat. Someone, Jing, is thanking you for your talk. Given that UDA and ShiftGAN is targeted in transfer from source to target, are you also considering deploying continual learning techniques into this topic?
Continual learning into this topic. Yes, definitely. Actually, we try a bit, and I just didn't. I saw the time is limited, so I didn't put them into my slides. So for example, we have tried this. Okay, not sure how it works, but anyway. So,
are you trying to share a screen?
I think, I don't know how it works, but anyway.
So you need to, if you unshare and then reshare the window that you want to share, that would work.
Okay. Stop sharing.
So essentially go back into sharing and select whatever you want us to see. If that's what you meant.
This one, yeah. Okay, can you see this one? The generalization.
Yeah.
Yes. So with the shift GAN, what we're thinking is, if we start with these two classes, right? And we build the shift GAN to learn the latent feature space transfer, the two GANs. And what about if we have a new classes come in? And can we using the GANs again and to include these new classes to automate the recognition on the target domain data? And we have done some experiment. As you can see, we assume different numbers of known activities, and we compare with only the traditional transfer learning techniques. None of the deep learning techniques will work because they are tied with the feature transfer with the classification. So there's no way you can break them. But just compare with ourselves. As you can see, on the binary data set, with the number of activities goes on, the accuracy does not change much. So maybe that works well on small dimensional feature spaces. The generated actually works well. They can learn the inherent feature space mapping. But on the accelerometer data, there's lots of variations here, and it's not very conclusive in terms of how these different numbers of old classes, the known activities, will impact on the new activities. So that's something we need to work on as well. And with continuous learning, that's very interesting. That's our recent topics as well. With continuous learning, for the normal network, you need to extend the last layer. So that most likely require you to do kind of fine tuning or change the architecture of the network. I'm not sure that's the answer you are expecting.
Well, I don't know if it answers Jing's point, but I think it gives a view on how you want to apply it. There is a follow-up question by Young. Well, thanks you for the presentation. Actually, he has two questions. It seems ShiftGAN requires 600 epochs. Is there any insight on how to reduce epoch training time so it can rapidly adapt to target users? That's the first question.
That example is very extreme we given here because that's the largest data we have. But with a small data set like we have on the B and the C, we don't need that many epochs. Let me find out how many we need on that one. So actually, if we look at the binary tasks, the epochs we need to converge is about 80. So it's much less. The example we are showing is from 400 to 200 dimension transfer. So 600 is kind of unavoidable in that sense. But actually, the training time is not that bad.
Good. Good news. So there's a second question. It said it's also interesting non-binary HAR data sets like search maps and datas. Does ShiftGAN work well when the sensor's input dimensions are different?
Yes, like we said here. So for the binary tasks here, and you can see the first tasks, they are on the same dimension. The second two are on different dimensions. Actually, the ShiftGAN works better on these higher dimensions than the other techniques. Much better than the other techniques, actually. The difference is much larger.
Very good. Thank you. I don't see any other questions. So thank you very much. I would like to thank you again with a clap. We will put the recordings online on our mobicenter.cl.cam.ac.uk webpage. So you can tell your friends to watch the presentation later if they haven't watched it, or re-watch it if you haven't understood something. I thank the audience, and there is another talk next Monday, 2 p.m. again. So I'll see you then. Thank you very much.
Thank you.